Okay, now we come to day 5 and I want to talk about a little bit performance and bottlenecks on the server side. So in this day, I want to first implement response caching in order to increase performance on the backend and service side. First thing first, let's dive into terminal and create a stress testing on our service. Here we are on the API. Let's fire up our API and run. Now our API is running on this port. Let's go to another tab, and in this tab, let's go to our folder. Now we create some stress test over our API. Let's name it stress testing. Okay. Let's give a name touch stress test. Right. Let's open the Visual Studio Code. Let's import request. I will write my stress test in Python. I mean, it could be done several tools, but in Python it will be very easy, maintainable and readable. Let's import random and import time, import concurrent features, and import argument parse. So my target is simulate several users, concurrent users, at the same time come to our website and list orders, create new orders, save it, edit some orders from the list, and go all the through pages inside the order page back and forth. So in the end, I am trying to simulate in an atomic time all those users coming to the website and how much time they spent while using this kind of user scenarios. So it will be very atomic and it will be very same time. So it will stress out our API endpoint and we will see our performance bottlenecks and how response caching will help to decrease complexity around our backend application. Let's give the base URL to running API URL Python like this. Then let's define some functionalities like listing orders, response requests get base URL /order skip. Why am I doing this URL definition like that? Let me remind you. I mean, the order and skip and take route is already defined in our Swagger URL. Let's check. Go to localhost 5205 Swagger. If you go to order page here, put order, skip and take. If you try that out, if you skip 10 and take 10, you'll take us with the 10 elements in a page to the second page. Here we are. So let's minimize and continue. Response raise for status and return response at JSON. I mean, easy. Instead of defining all these URLs in a Postman or any other type of software or some kind of unit tests, using Python to this manner is a good choice. Let's define get random page. For example, user can select a random page and first page would be this. And the total count can be taken from the first page. Let's say first page get total count with length of first page get items and array. Let's close all the parentheses, and page count will be first page get page count 1. Page index can be random, it's an integer between 0 and page count. Page count -1 means 0 index page count and element. So let's calculate our skip. Would be the page index multiplied by take. So, and the page will be list orders method or with this calculated skip and take. And let's return the page. Okay, get random page function is ready too. Let's define an update order random function. Update order random. The original order will be defined like this: order dot copy. This will be the copy, an instance of our actual order. So the modified order will be another copy. Let's randomly modify the freight property of that particular order. Modified, first get the modified freight value, or if it is 0 or null, again make it 0. And let's add a random uniform value between 0 and 10 with digits 2. Okay, now the freight value of the order on the modified is modified basically. Now we can say requests put, because the put right here is the update of the order. The HTTP put is the update of the order. Okay, let's requests put again base URL slash order, and we can give JSON modified variable, and we can resource status, and we will return the original. Or we can return the modified, whatever you wish. Let's write a create order function. By the way, what we are doing is basically we are creating another client, a Python client to our service, along with React client. You can think like that. So we are defining some test cases and the client functions of our API inside the Python. New order with order ID, zero, and response requests. Now it needs to be a post, and after the post is the same like update and response. It's for status, and we will return again response. Yes, like this. Let's write a find order. I want to simulate the user actions. Think about it. Our application doesn't have a search capability, so the users will search with their eyes and ears, basically. So that makes they will traverse all the pages until they find their orders. So basically they will next, previous, and select some numbers from the screen. Remember, from the user interface. So how can we simulate this one? Think about it. If I find order, the order ID with 0 will start. While they find what they are looking for, the users will traverse the pages. Page will be list orders of skip and take, and items will be the items actually what page brings. Table will be the item of the page, like this, and for each item they will look for the order ID, and we are simulating the same behavior that user does with their eyes. Until the order ID is the seek order ID, they will check, and if they find out their order, they will click. But first we need to return that order here. If not, yes, the user will go to another page, like skip all those orders, and if skip is greater than equal page get total count, return none, means you are end of the page. This was the find order. Let's define also a delete order function, because maybe in your user story we can create and delete some orders. Delete and base URL with order ID, like this. Raise for status. That's it. That's the delete order. Let's define our user story, because we have all the client methods: delete, find, create, update, and list. So for the user story, let's define page size with 10. Page first, let's get the random page take, and the order will be a random choice. Look, this choice a random element from a non-empty sequence. We can use this page get items page, and if page or something or none. So if the order is none, if not order, and we return. If you found our order like this, order ID, we will give this page element count 10 as a parameter to define the order, and this will be the step 1, finding an order inside that page. If you find the order, let's go to step 2, edit order. Original is update order random order. Let's put a small gap. I think I forgot import time. Let's import it. So we can go to step 3. Step 3 will be refetch and revert. It's updated. Create a variable called updated with request get that order is JSON requests put. Let's copy paste that base URL of order, and JSON would be original, and we will raise for the status. So this will be refetch and revert. Step 4, create new order. Created will be stored to the created variable. Let's call the create order that we wrote previously, the updated one from previous step, and let's take the ID like this, create with order ID. Now we have the ID. Let's in the step 5 make the user search that created order, and find order with the new ID and page size take. This is the order that we found into the variable found. And step 5, delete that order. Sorry, step 6, delete the order. Delete order with new ID. So the order is created, manually searched in the pages and delete. So this hurdle will very good example to concurrent workload on the backend service. Let's also measure the time service, all the requests and responses, and let's take the iteration count as a parameter, and defaultly we will give the page size 10, and let's call it a start variable with time. Let's try our user story with the page size except any exception as e on exception. Let's print the exception like that. Iteration error e. That's our exception handling. Elapsed time is time minus start multiplied with 10,000, which means it's a millisecond. Let's print. Let's copy paste it from here. Print iteration completed. Iteration number completed. In elapsed time, we can format it like elapsed with 2 decimals and millisecond. UF means two decimal floating point. So, and we can also return the elapsed time from here. That's it. Let's define our main entry point. Main e equals parse argument parser. Description equals nothing. E add argument. We can say C, and it could be concurrency. Will be the first parameter. Type is integer. Default can be 100. So help equal to number of concurrent threads. Another argument will be the iteration count. Now make it I, and longer version will be iteration. Again, default is 100 and it's an integer, and as a help we can write total iterations per run. Arguments are b parse. Okay, and we can get the concurrency as a parameter from args. See, and we can take iteration as a parameter from args iteration. Times as an array, we can take it, and with concurrent library of features of Red Bull executor, max workers would be the concurrency as executor. Features would be executor submit timed user story of iteration, which is I for I in range iterations. Should be iterations here, iterations, yes, like that. And instead of iterations, we can write iterations here. Let's see, fixed it. Means the REPL executor runs timed user story functions simultaneously as many as concurrency count. So in this manner, we will start, if with the default values are used, 100 iterations with 100 CPU threads. Let's for feature in concurrent features as completed here features. Every completed feature should have an elapsed time, so we can get it from the result, because all the timed user story methods return the elapsed time, so we can add to the times we will use afterwards. If all the threads are done and if the times are something, then no, so we can calculate the average time. Average is sum of times divided by length of the times, and we can print f average execution time is average, again 2 decimal floating point, millisecond over length of times, okay, iterations. In the end, if main equals main, which is the entry point, main run the main semicolon. Okay, that's our stress testing Python code. Let's run this code in terminal. Let's view terminal directly right here. So let's say Python 3 stress test pi. Let's run it. Oh, a small mistake. Concurrency in the line 94. If control and mouse click, it will automatically goes that line, which is perfect. We fixed our mistake, and let's run it again. We forgot to save. Let's run it again. As we can see now, the iterations are completing like 58, 60, 62 seconds. I think we are coming to an end. One time it's overflown. Yeah, it's broken. It's too much, I think. Let's make the test a little bit smaller, like concurrence 10 with iterations of 10. I mean, 100 concurrent user is too much for my laptop, I think. Yeah, 10 concurrent user for my laptop is much nicer. Okay, that's it. Our stress test is complete. But let's go to our API code, like Node.js API, and implement some response caching. Here we are. So it's very easy. Let's go to Untitled API controller base that we have written previous sessions. So here, let's define for the get a response cache. Response cache vary by header with user agent, and duration of get sets the duration in seconds which response is cached. Yes, we can catch it for 10 seconds, and we can do the same for the paginating function, and we can do it for the single identity function. Yes, because we have an abstract entity API controller base, all the controllers have that ability to do response caching now. Customer, category controller, everything driven from the entity API controller base. We don't need to touch that controllers anymore. But we need to touch the program, I think. Here we are. Before we are running the application, we need to add use response caching turned on. Okay, now the response caching is turned on. Can go here and dotnet run. It's building. Now it's running. On the stress testing side, let's run item 3 stress test PI with concurrent 10 users with iterations of 10. In first run 17 seconds, so I mean it looks worse in first glance, but if we run the stress test again, I mean because the initial time, yes, now average time execution is 6.7 seconds. If we check the before, it was 10. I mean response caching gives us 3 seconds more. If we run it again and again with more iterations, we will see it gets better. Look, now it's 5.9. So let's make another test, because right now we are testing read and write. What about just read? If we go to our test and comment out all the editing and deleting steps, just left with only the read-only functions like find order, and let's go to our program and comment out response caching. So let's measure first without response caching. .NET run, and on the stress testing side, run 10 concurrent user with 10 iterations. Let's disregard first iterations and clear the screen and run it again and take the number. Yeah, with 10 iterations, we can see now 1 second for 10 iterations. I mean, approximately 1 second. 961 milliseconds, 1 second. So let's go and activate the response caching and run it with response caching now. Yep, it's running now, and we don't count the first iteration, and the second one and the third one. As you can see, if we just left with the only read-only functions, the performance not getting better. So we need to, that means this is not a magic one. Okay, this needs to be decided how to use and how to not to use. Sometimes this kind of catch can a performance bottleneck too. Let's see. If we turn off the response caching again and stop this and rerun it again, when we change now to 20 concurrent users with 20 iterations, we will see much more longer time. But if we disregard the first iteration and run it again, we will see without response caching, it is counted to 1800, means I mean approximately 3 seconds. So let's, for this bigger test, turn on response caching here and rerun and rebuild our API and go stress testing. Don't forget the average execution time without response caching was 3 seconds. Now we will run with response caching, just read-only functions, no write. By the way, the first iteration was much more faster than the initial first iteration, but let's see the second iteration. Now it's 3.3 again. Now for the third one, it's 3.5. You see, some iterations are much more faster because the response caching was much more faster. But now, if other iterations, are getting slower. I mean, this test only runs on my computer, and every iterations depends on my CPU times, so it's not so objective. But if you check further, now it's 2.5. I mean, yes, response cache in this manner gives you some kind of versatility over concurrent user count. If the concurrent user count are much and your service will running long time with that amount of concurrent user, yes, you will need a response cache. In next upcoming days, we will check another type of distributed cache like Redis cache, I think. So at that moment, we will see how we can increase this server-side performance with this kind of refactoring with cache. That's it for today. Thank you for joining. Please subscribe and like this video if you actually liked it. Bye.